So from this formula, in terms of sign convention, we can conclude that object and image always lie on the same side of the focus in case of spherical mirrors. Hello everyone, this is Bhavesh Kriplani and welcome back to this wonderful series, Fantastic Concepts and Where to Use Them. So today's video is based on ray optics. We are going to learn how to draw the graph between U and V in case of a spherical mirror, in case of lenses and spherical refracting surfaces. So in total there are 12 graphs, right? 6 of them are between 1 by V and 1 by U. Okay, so on the vertical axis you have got 1 by V, on the horizontal axis you have got 1 by U. Okay, out of these 6 graphs, 2 belong to the mirrors, 2 belong to the lenses and 2 belong to spherical refracting surfaces, and all of them are straight line graphs and they are easy to understand, so I'm not discussing them. Okay, what I'll be discussing is the graphs between V and U. Okay, so again there are 6 types of graphs between V and U. Again 2 of them belong to mirrors, 2 of them belong to lenses and 2 of them belong to spherical refracting surfaces, and they are all curved like this. So this is what creates confusion, like in which case what type of graph to draw. Okay, so there's a very easy trick, a very easy formula that was given by Newton himself, and it will help you understand these graphs easily. So let's continue. So Newton gave a simple formula, we call it Newton's formula. Okay, so first of all we are going to understand a simple version of this formula. Alright, so let's first look at spherical mirrors. So here I got a concave mirror, right? This is the principal axis, focus, object and the image. Now let's say the distance of the object from the focus is equal to x. Similarly the distance of the image from is equal to y. Then xy becomes equal to f square. This is called as in Newton's formula. We can apply this formula in case of convex mirror as well. The focal point is inside the mirror, but still we can measure the distances, right? X for the object, y for the image, and again you get xy equal to f square. The derivation is very easy. Now in case of lenses, in the case of lens we have got 2 focal points, one on this side and one on the other side, right? One focus is called as the first focus and the second one is called as the second focus. What are their specialties? So the first focus is the position where you keep the object for image to be at infinity. Okay, and the second focus is the position of the image when the object is at infinity, right? So for the object you measure the distance from the first focus, and for the image you measure the distance from the second focus. Distance of object from the first focus is x, distance of image from the second focus is y. Then again you get xy equal to f square. So till now what we saw was the Newton's formula in simple form. Okay, but what would happen when you apply the sign convention in the Newton's formula? Okay, so in case of mirror, let's say the pole is taken as the origin and all the distances are measured from this point. This direction is positive, that direction is negative, and u, v and f are what? Positions of the object, image and the focus. Since right now all of them are in the other direction, so u, v and f, all of them are negative. Okay, now what about x and y? So x and y are the positions of the object and image with respect to focus. That is, we are measuring x and y taking focus as the origin. In that case again, right now x is negative, y is also negative because both of them are in the negative direction. Okay, and then if I apply simple math, I will get x to be equal to u minus f and y to be equal to v minus f. Remember that in this condition x and y both are negative. Now when you apply Newton's formula, so on the right side of the equation x is negative, y is negative, together they form positive product. On the left side f square is again positive, correct? So xy equal to f square. Now comes a very important conclusion based on this. Because this side of the term is positive, f square is always positive, so the right side of the equation should always be positive. That means if x is negative, y should be negative. If x is positive, y should be positive. So right now object and image, both of them are on the right side, so x and y both are negative. So in case the object comes on this side of the focus, in that case x will become positive. Then image should also come on this side and y will also become positive. Okay, if object is kept over here, image is formed over here, magnified image, right? So from this formula, in terms of sign convention, we can conclude that object and image always lie on the same side of the focus in case of spherical mirrors. Now let's look at this animation for the concave mirror. So here you can see that the object and image are on the same side of the focus. Let me change the position of the object, and as you can see, they are still always on the same side of the focus. But what if I change the position of object with respect to focus? So when the object is brought on the other side, you see that the image is again on the same side of the focus as the object. Here both of them are on the negative side, and here both of them are on the positive direction of the focus. Alright, now same thing goes for convex mirror as well. For the convex mirror, this is your focal point, right? And as you can see, the object and image are on the same side. So if I change the position of object, you see that the image is still on the same side of the focus as the object. Okay, now what would happen in case of a lens? Okay, so now we are measuring the distance from the center of the lens. This is negative direction, this is positive direction. Again, u, v, f1 and f2 are what? Positions of object, image, first focus and second. Now comes the important point. The first focus for convex lens is in the negative direction. So f1 will be negative. Okay, f1 will be negative. Similarly, second focus is in the positive direction. So f2 will be positive. f1 and f2 have same magnitude, but they have opposite sign. Now, when it comes to the measurement of distance of object and image from first focus and second focus. So in that case, when you take the object, you are measuring the distance from the first focus. So take the first focus as the origin. When the first focus is the origin, then x is negative. In case of image, take second focus as the origin. So while measuring distance from this point, y is positive right now. Okay, so applying simple mathematics, again x will be equal to u minus f1 and y will be equal to v minus f2. Okay, they both have different origins. Now when you apply Newton's formula, so xy will be equal to f1 f2. See, now comes the important application of sign convention. f1 right now is negative and f2 is positive. Both of them have same magnitude. So when you put the values, you get f1 f2 equal to minus f square. Now the square term is positive, but we got a negative sign. So this side of the equation is negative. That means multiplication of x and y should be negative. And that means x and y should always have opposite sign. Okay. Now, this means when object is on the negative direction of first focus, image should be on the positive direction of second focus. Alright, object and image are always in the opposite directions of the first and second focus respectively. This is valid in all the cases of real object and virtual object. Now what about a concave lens? So again, this is the origin. We are measuring the distance with respect to this origin. So first focus is in the positive direction, so f1 is positive, and second focus is in the negative direction, so f2 is negative. Okay, now since first focus is taken as the reference point for object, so from here we are measuring x in negative direction. So right now x is negative. Similarly, y is in the positive direction, so it is positive. Now look at this equation. Again, f1 and f2 have opposite sign but same magnitude. So f1 multiplied by f2 will give me minus of f square. Again, this is negative. Square is positive, but we got a minus sign. So this side of the equation is negative. That means again x and y should always have opposite sign. So when object is in the negative direction of first focus, image should be on the positive direction of second focus. Again, this is valid for all the cases of real and virtual objects. Again, let's look at the PhET animation for the convex lens. Okay, so right now, as you can see, the object is on the negative direction of first focus and the image is on the positive direction of the second focus. So let's move the object and see what happens to image. As you can see, when the object is on the left side of the first focus, image is on the right side of the second focus. But when object is on the right side of the first focus, then what happens? The image has gone to the left side of the second focus, right? This is your second focus and image is on that side. So now look at this animation for concave lens. This is your first focus and this is your second focus. Right now, with respect to first focus, object is on the left. Okay, and with respect to second focus, image is on the right. Okay, so object and image are on the opposite sides of the corresponding focal points. Okay, now observe when I shift the object, what happens? See, for any position of the object, the image is on the right side of the second focus because the object is on the left side of the first focus. Okay, so now that you have understood the Newton's formula using sign convention, let's use that to draw the graphs. Okay, so first of all, we will start with concave mirror. So we have the Newton's formula xy equal to f square. So I'm replacing x with u minus f, replacing y with v minus f. So I have got this formula and I will be using this to draw the graph. Okay, so let's first draw the coordinate axis. So this is the vertical axis which belongs to v. This is the horizontal axis which belongs to u. Now if we want to draw the graph for uv equal to f square, okay, this is a positive constant. What is this? This is a positive constant. Okay, this is a positive constant. So the graph for this formula will be a rectangular hyperbola which would look something like this. This would be your graph. Okay, this is the graph for this equation. Now suppose I want to shift the origin for this graph to the point f comma f. So shift origin to f comma f. Okay, so in that case what will happen? My axis will be shifted with a new origin f comma f, and for concave mirror f is negative, so this is x coordinate is negative and this y coordinate is negative. Okay, so the point f comma f will be somewhere over here. This is my point f comma f, right? F is negative, y is negative, so this point is in the third quadrant. Now using this point I draw my new axis. Okay, and again I draw my hyperbola. So the hyperbola will look something like this. And remember the important point, the graph over here should pass through origin. Okay, now another important point to understand. If you join these 2 points, origin and the point f comma f, and extend the line, so this point over here will be equal to 2f comma 2f. So this is the easy way of drawing the graph for concave mirror. Okay, now let's apply the same concept in case of convex mirror, right? So again I have xy equal to f square, x equal to u minus f, y equal to v minus f. Okay, again let's draw the coordinate axis. So this is the vertical axis. Okay, and this is the horizontal axis. And if I draw the graph for uv equal to f square, this is a positive constant again, right? So my graph will again be a rectangular hyperbola like this. Okay, but according to this formula I want to shift the origin of my graph to f comma f. Okay, now shift origin to f comma f. In that case I need to draw the axis again over here. Why at this point? Because this point f comma f will have positive coordinates. Okay, for convex mirror f is positive. Okay, so f comma f is in the first quadrant, and again when I draw the graph would look something like this. And remember that the graph should pass through origin, and again when you join these 2 points, this point over here will be 2f comma 2f. Okay, so a very easy way of drawing the graph for the mirrors. Now let's understand convex lens. So xy equal to f1 f2, and my formula will be converted to this form: u minus f1 instead of x, v minus f2 instead of y, equal to minus f square. Okay, so when you're drawing the graph between u and v, this is my vertical axis, horizontal axis, v and u, and if I draw the graph for uv equal to minus f square, here I got a negative constant. Okay, so in that case the rectangular hyperbola would be like this. Okay, for positive constant hyperbola is like this. Okay, but since we have got a negative constant over here, hyperbola will be like this. But again I need to shift the origin. Shift origin for convex lens according to this formula. Okay, u minus f1, v minus f2, so I have to shift the origin to f1 comma f2. Now for convex lens, f1 is positive. Okay, so f1 is negative, so here I get minus f, and for f2 I get plus f. Okay, so I have to shift the origin to this point. Let's do that. So this point will lie in the second quadrant over here. Okay, so these are my coordinate axes according to shifted origin. This is minus f comma f. Now when you draw the graph for this formula, so the graph would look like this. Okay, a rectangular hyperbola which is passing through origin at this point. And just like what we did in case of mirrors, here also when you join the origin and the shifted origin, over here you get the point minus 2f comma 2f. Okay, so this is the graph for convex lens. Now what about the concave lens? So in concave lens also we will follow the same process. Okay, so this is v, this is u. For uv equal to minus f square, my graph should look something like this. But according to my formula, I have to shift the origin, to f1 comma f2. Again, f1 is what? f1 will be minus f and f2 will be plus f. But for concave lens, f itself is negative. Okay, for concave lens, f itself is negative. So that means the x coordinate over here, okay, the x coordinate over here is actually positive. Okay, negative multiplied by negative will give me positive. Similarly, the y coordinate over here will be actually negative. So you are basically going to the fourth quadrant for shifting of origin. So I will draw the coordinate axis over here. This is my point minus f comma f, but f itself is negative. So now when I draw my graph, so the graph again passes through origin like this, and this will be my rectangular hyperbola. And again when you join the origin and the shifted origin, this will be my point minus 2f comma 2f. Obviously my graphs are not accurately drawn. I will show you them again on the Desmos. Now comes the final part, that is spherical refracting surfaces. Now remember one thing, spherical refracting surfaces are just like lenses. There are two focus, first focus and the second focus. First focus is the position of object for image to be at infinity, and second position is the position of, sorry, second focus is the position of image when object is at infinity. Okay, so here is the formula for first focal point and second focal point. As you can see, they don't have same magnitude, so the distance of the two focal points from this pole is actually different now. Okay, and again we have got two systems, converging system and diverging system. In case of converging system, first focus will be on the negative direction, so f1 will be negative, f2 will be positive. In case of diverging system, f1 will be positive and f2 will be negative. Rest all is exactly same like lenses. Okay, only difference is in the magnitudes of f1 and f2, rest everything is same. Okay, f1 positive, f2 negative, or f1 negative, f2 positive, they always have opposite signs. And the formula that we are going to use is also same as that of the lenses. This is my Newton's formula for spherical refracting surfaces. Okay, so following the same process as that of lenses, when I want to draw the graph for converging system, okay, this is V, this is U. First of all, if I draw the graph for UV equal to F1, F2, again F1 and F2 always have opposite signs, right? So this is a negative constant, so the graph would be like this, exactly same as that of lenses, a rectangular hyperbola in this fashion. But I want to shift my origin, shift origin to f1 comma f2, because here I got u minus f1 and v minus f2. Okay, now comes the important point. For converging system, f1 is negative, f2 is positive. Okay, for converging system, this is negative, this is positive. All right, so I need to shift the origin into the second quadrant. So this is my f1 comma f2, and now based on this new coordinate axis I can draw my graph. Okay, so the graph will again pass through origin, and obviously when you join them together, this point will be 2 f1 comma 2 f2. Okay, now you guessed it right, when you want to draw the graph for diverging system, then your coordinate axis needs to be shifted in the fourth quadrant. Okay, axis will be shifted over here, and your graph, okay, axis is over here, the graph would look something like this. Okay, so let's look at all these graphs together once again. So now let me show you all the graphs one by one on the Desmos graphing calculator. So first of all, let's start with the concave mirror. So in case of concave mirror, let us say that the focal length is -6. Okay, so my origin will shift to this point over here, -6 comma -6 in the third quadrant, and this is how the graph looks like. Now one more thing I have added over here, that for real object the graph will be a solid line. Okay, but for virtual object, that is when u is positive, here I have taken a dashed line over here. Okay, for the graph. So this side is for the real object and this side is for the virtual object. And as you can see, the line joining origin and the shifted origin passes through 2f comma 2f, that is -12 comma -12. Okay, I can change the value of focal point. Okay, but still for the concave mirror. So this is how the graphs would look like. Okay, now suppose I want convex mirror. So for convex mirror, I need to go into the first quadrant. So the shifted origin will be at 6 comma 6. Okay, and again this line joining over here will pass through 2f comma 2f, that is 12 comma 12. Again for real object, this is your solid graph, and for virtual object we have got a dashed line over here. They all will satisfy the Newton's formula. Okay, now if you want to look at the lenses, so for convex lens, this is how the graph would look like. Okay, the origin is shifted to the second quadrant. Okay, and this is my zone for the real object, and this is the graph for the virtual object, right? If I want concave lens, so this is how my graph should look like. Okay, this is the zone for virtual object, and this is the graph for real object. Then if you want a converging spherical refracting surface, now first focus and second focus are not equal, so this is your graph for convex lens, and if I decrease the first focus slightly, this is now the graph for a converging spherical surface. On this side we have a real object, okay, u is negative, and on this side we have virtual object, so u is positive. All right, and if you want a diverging spherical surface, this is how my graph should look like. Okay, if you want to play with this graph, I am sharing you the link in the description over here. Don't forget to like this video, subscribe to the channel, click on the bell icon, and share this video with everyone.